Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Samaresh Bera, and he will be speaking on network slicing in 5G edge networks with controlled slice distributions. Dr. Samaresh Bera is a C.V. Raman postdoctoral fellow at the Department of Electrical Communication Engineering, IISc. Before that, he was a visiting researcher at the British Telecom India Research Centre at IISc. He also worked as a research engineer at Indria Sofia Antipolis, France, in a joint collaboration with Nokia Bell Labs. He obtained his PhD and MS degrees from the Indian Institute of Technology, Kharagpur, in 2020 and 2015, respectively. He was recognized as a young researcher to attend the 5th Heidelberg Laureate Forum, Germany, in 2017. He also received the IEEE Richard E. Birwin Scholarship for his outstanding contributions to the IEEE in 2017. His current research interests include software-defined networks, network function virtualization, and 5G network slicing. Before we move on to the talk, we would like you to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Samaresh or type them in the chat box, and we'll moderate with him. So over to you, Samaresh.
Hey, can you hear me?
Yes.
Yeah, hi, thanks for the nice introduction. Good afternoon, everyone. I'm going to present our recent work on network slicing in 5G edge networks with controlled slice redistributions. And this is the joint work with Professor Nilesh B. Mehta as part of my postdoc research. So in this talk, I will present this talk divided into two parts. In the first part, I will discuss, briefly introduce the software-defined networking and network function virtualization and the network slicing in 5G, also the issues and challenges in network slicing. Then I will move to the second part, where I will discuss our proposed scheme on network slicing in 5G edge networks that consist of problem statement, proposed solution, and numerical results. And then I will touch upon our the works we are doing currently in our lab. So the software-defined networking, it is basically the restructuring the current network infrastructure by separating the control and data planes from the traditional forwarding devices. So by separating this control plane, we have the centralized control of networking devices in the network, and we have the global view of the network using the SGN technology. So if we look at the figure here at the SGN architecture, we have three different planes: data plane, control plane, and application plane. So at the data plane, we have the forwarding devices that forward traffic based on the control logic decided by the control plane. So at the control plane, we have network operating system, and at the application plane, we have different applications running on top of that. So for example, security application, routing application, traffic engineering, or any other application. So based on this application specific requirement, the network operating system, so here we call it as SDN controller, the controller instructs the forwarding devices how to forward the traffic in the network. And we note that we have two well-defined application programming interfaces. One is between the application plane and the control plane, and the other one between the control and data plane. So you might be heard about the OpenFlow. Also, the advanced protocol like P4 protocol are being used. Is this as the interface between the control plane and the data plane? So using the SDN technology, we have few advantages. For example, real-time programmability of networking devices, And also we have fine-grained traffic forwarding. So here the real-time programmability means that the SGN controller can instruct the forwarding devices how to forward the packet on receiving a new packet in the network. So, and also we have the global view. So for example, the routing application, suppose it is running on these three forwarding devices. So we have one global view. This is the subnetwork. We have for traffic engineering, we have another global view. And for other application, we have another global view of the network. So here I have presented examples of traffic forwarding in SDN. So we have three different examples. Let us consider Ethernet switching. So in OSDN, we have, this is called flow rule. So here we have different match fields. For example, switch port, MAC source port, MAC destination, Ethernet type, and so on. And we define the rule that if the MAC destination address of the received packet is something like this, then the desired action is the packet should be forwarded to port 5. So similarly, we can have the rules for IP routing. We can have the rules for application, different applications, for example, firewall. So if the TCP destination port is 22, the desired action is it needs to be dropped. Another technology is network function virtualization. In short, we call it as NFV. So here, it uses the virtualization of physical resources. So through this virtualization, we can place the network functions as software modules. And once we have this service-based architecture, we can have independent networking that is independent of vendors, products, and technology. So if we look at the example here, we have the dedicated hardware that are being used in the current network. For example, router, firewall, optimizer, for example, video optimizer when we have video traffic, or we can have load balancer. So all these are special purpose hardware devices that are being currently used in the network. However, using this NFV technology, we can use the general purpose hardware, and the hardware resource is virtualized using some hypervisor. And on top of that, we can place these network functions as software modules. For example, at the same hardware device, we can place a router, firewall, optimizer, or we can run different security applications. So this enables us to reduce the CapEx and OpEx to the network operators. So if we look at the SGN's NFV architecture, we have three different orchestrator or rather the managers. So one is the NFV orchestrator, then we have virtual network function manager and virtual infrastructure manager. So this particular architecture is being used for the network slicing. So the network NFV orchestrator, it orchestrates the entire network based on the service request received in the network. Then we have the virtual network function manager. It manages the virtual network functions, including their life cycle. And then we have the physical network that is managed by the virtual infrastructure manager. So at this network function virtualization infrastructure, we have two layers. One is the physical resource, and on top of that, we have virtual resource. So in between, we can use different hypervisors to virtualize the physical resources. The VNF manager controls the VNF in the network, and each VNF again further controlled by one entity manager. So this entity manager controls the operation within the VNF, for example, fault management or some other application. So using this architecture and the SGN technology, we have different advantages. For example, real-time programmability we can control the fine-grained traffic forwarding in the network. We have the global view of the network in the presence of SGN technology. We can have vendor-independent networking for traffic routing as well as function placement in the network. We have like ease of dedicated hardware for network functions. Also, finally, we have the reduction of CapEx and OpEx to the network operators. So if we look more closer, let us understand this when we combine SGN and NFP together. Let us say we have one network, which is presented as a graph here, and we want to support one application that needs two network functions to be executed. One is the firewall and the other one is the optimizer. So we need to place these two network functions in the network, and the network is facilitated with some compute and storage resources. So let us say we have two facilities, facility 1 and facility 2. So the firewall network function is placed at the facility 1 and optimizer is placed at the facility 2. So this placement of network functions is taken care by the NFP technology. Whereas the SDN maintains the routing of traffic through these VNFs. So for example, the routing path is from A, C, D, E, F. So, and another thing is that we need to maintain the service function chain. So here, the service function chain means firewall needs to be executed first, then the optimizer. So this SDN takes care of this fine-grained traffic forwarding through the VNFs. So now we move to the network slicing, because network slicing uses the concept of this SDN and NFP technology. So the network slicing is the creation of multiple logical networks, and each logical network is customized to provide specific services based on the requirements. So if we take an example, let us say we have the softwareized network. That means that is entire network resources are virtualized. And we can have three different logical networks, one for mobile service, another for massive IoT, and the other for critical IoT. So we can create three different logical networks, that is the network slices, to provide differentiated services. So here is another example. We have physical network. The physical resources are virtualized, and we have three different slices, slice 1, slice 2, and slice 3. And all of them have their logical view of the network. And we have three different network instances that are created based on the applications. So the next question comes into our mind that why network slicing in 5G? So if we look at the 5G use cases, we'll see that it has diverse QoS requirements. So in terms of bandwidth, latency, reliability, and device density. So if we look at the example figure here, so we are all familiar with this figure that we have broadly three different applications: enhanced mobile broadband, massive IoT, and ultra high reliability and low latency application. So to support these diverse requirements, we need adequate technology to meet such requirements. So for example, enhanced mobile broadband has very high bandwidth, up to 1 Gbps or even in the order of 10 Gbps. For ultra high reliability and low latency, we have latency as low as 10 millisecond. Now people are talking about 1 millisecond. Also, we have reliability that is up to 0.59%. And for massive IoT, we have up to millions of devices per square kilometer. So to meet such diverse QoS requirements, we can create different network slices based on the applications, and those different networks are customized based on the QoS requirements of the applications. So if we look closer to the 5G system architecture, we have different network functions. For example, network slice selection function, access and mobility management function, session management function, then UPF is a user plane function, and so on. So all these functions can be placed as virtual network functions in the network. So if I divide it into two planes, one is the control plane and the data plane. So all the control network functions that are part of the control plane, and we have the UPF, user plane functions, that is part of the data plane. So we can place all these network functions as virtual network functions, and they communicate with themselves using the HTTP protocol, the simply get and post method. So we don't need any special purpose protocol to communicate between the network functions in the 5G system architecture. And this network function selection is very dynamic and flexible. So the dynamic and flexible means we can increase the number of network functions associated with a particular slice. So for example, we have heavy traffic load to the network slice. So then we can increase the number of user plane functions. And when the traffic is low, we can reduce the number of user plane functions in the network. So similarly, the number of control plane functions also can be increased or decreased, like scale up or scale down, depending on the traffic load to the network slice. So this service-based architecture of 5G system enables network slicing. So yeah, obviously we have different challenges in network slicing. So the obvious questions are like, first one is the VNF policy. So as I mentioned that the network functions can be placed as virtual network functions. So the first question is whether these VNFs are shared or isolated. So in the first example, if we look here, the scenario one, let us say we have three regions. One is the radio access network, then we have the edge, and then finally we have core. So we have two different slices that are completely isolated from each other. So we don't have any problem, but we need more physical resources to support such slice placement. However, if the VNF is shared among two slices, then so let us look at the example here, the scenario 2 and scenario 3. So here the VNFs, the network functions, is shared between two slices. So here the edge network is shared among two slices, slice B and slice C, and here the RAN is shared among between slice A and slice C. So when these VNFs are shared among two different slices, so the question is how to ensure the desired performance, because the traffic load on one slice will affect the performance of another slice. And another question is from a network operator viewpoint is who will control these shared slices. The next issue is VNF placement. So the VNFs, virtual network functions associated with the slice, needs to be placed either at the edge or at the core network. So where to place these virtual network functions given the network resources and service requirements? For example, we would be interested to place the virtual network functions associated with that ultra reliable and low latency applications at the edge, whereas the mobile broadband applications, the VNFs associated with the mobile broadband applications can be placed at the core. So we need to decide in real time that where to place these VNFs given the network resources and service requirements. Then the another question is like how to route traffic through the VNFs, because as I mentioned earlier, we have to maintain the service function chain, and also we need to fulfill the required bandwidth associated with the slice. So, and finally, we have traffic classification. So the traffic mapping to individual slices in the network. Because once the slices are created in the network, we need to map the traffic from the users to the respective slices to meet the service level agreements. Yeah, so any questions? Because next I will move to the second part, to the proposed scheme. Okay, so once we have the basic idea of network slicing, in this particular work, we have focused on 5G edge networks with controlled slice redistribution. So we focus on the edge network with the reason is that the placement of network functions as the edge network reduces network latency. So our aim is to maximize the total revenue to the network operators by serving the slice request. We have some limitation that we have limited compute and storage resources at the edge compared to the central cloud. And the obvious solution or the answer is that which request we want to serve at the edge. So let us look at the problem, the system model and the problem statement. So we are given a 5G edge network that consists of edge clouds that are facilitated with some compute and storage resources. And these compute and storage resources are used to host the virtual network functions associated with the slice request. So here the VNFs, or rather the network functions associated with the slice request means, suppose we want we have a slice request related to the video application. So we might be interested to have the video optimizer as one network function, another as firewall, another VNF is as firewall. So we need to place these virtual network functions associated with the slice request. Then we have non-edge cloud nodes that simply forward the traffic in the network, and we have links between the nodes with certain bandwidth to forward the traffic. So let us look at the example figure here. Let us we are given a network that is presented as a graph, and the nodes C and E are facilitated with some compute and storage resources. And we have two such facilities. One is Edge Cloud 1, the other one is Edge Cloud 2. The nodes A, B, D, F are the non-Edge Cloud nodes. They simply forward traffic in the network, and we have the links in the network. So for example, the link between node A and C have bandwidth 5 to forward the traffic. We also have slice requests with bandwidth, compute, and storage requirements. These compute and storage requirements are calculated based on the network functions required by the particular slice request. And the slice request is also associated with a reward if the request is served by the network operator. So in such a setting, our objective is to maximize the total reward. So if we look at the example here, let us say we have initial slice request assignment where we have two slices. One is in the red color, the other one is the green color. So the red color one is assigned to Edge Cloud 2, and the green color is assigned to Edge Cloud 1. On receiving a new request, we see that the assignment changes to admit the new request. So the green color, which one earlier assigned to Edge Cloud 1, now is assigned to Edge Cloud 2. And we are able to admit a new slice request that is assigned to Edge Cloud 1. So we see that this slice redistribution helps to admit more number of requests in the network. So here the redistribution we mean as the VNFs that are placed in the at the edge clouds needs to be migrated from one place to another place. However, this active slice redistribution entails significant operational cost as follows, like migration time, interstate dependency, and additional bandwidth. So when we say migration time, it means that the VNFs associated with the slice request needs to be migrated from one location to another, one edge cloud to another edge cloud. So in that case, this migration process involves some computation time. Also, the VNFs can be the migration process can be stateless or stateful. So in case of stateful VNF migration operation, we need to consider the interstate dependency. Finally, we also need additional bandwidth to migrate the VNF from one location to another. So in this work, our contributions are as follows. We allow active slice redistribution in the network while controlling the slice redistribution in the network. We introduce a penalty function to take into account the effect of active slice redistribution. And we note that this active slice redistribution is not considered in the literature. Further, we design two comprehensive cost functions that takes into account the more generalized networking resources such as bandwidth, storage, and compute. And then we also consider the multi-hop traffic routing in the edge network, unlike the works proposed in the literature. So in this work, we address three fundamental questions in network slicing: whether to admit a slice request, and then if we admit a slice request, which edge cloud to select to serve the request, and finally, how to route the traffic associated with the slice So consequently, we formulated the problem as an optimization, constant optimization problem, where we have the maximization of reward minus a redistribution penalty. So the reward here, the first term, zeta r is the reward associated with the request, and xkr is the binary variable that denotes whether request r is assigned to edge cloud k, minus the penalty term, where sigma is the penalty factor, and the redistribution penalty, we pose it as a function as the current assignment and the previous assignment. So here xkr is the current assignment of the request r to the edge cloud k, and tilde x is the previous assignment. So if the assignment changes, then we have some penalty. We also have the following constants, like the storage constant and compute constant at the edge clouds. So the utilization of storage and computing resources at the edge cloud should not be greater than to the available, like the capacity of the edge clouds. Then we have the bandwidth constant at the links. Further, we have the assignment constant. Here we note that each slice request is assigned to maximum one edge cloud. So it cannot be divided into two edge clouds. We have the binary variables. One is the assignment to the edge cloud. So request R is assigned to the, whether it is assigned to the edge cloud K, and YIJR, that is whether request R link IJ is used to route the traffic associated with the slice request R. And finally, we have the flow conservation rule. So first one is the related to the source. The second one related to the selected edge cloud. And for intermediate nodes, we have 0. So here, if the edge cloud is not selected, then it would be 0. So it would act as an intermediate node. So this optimization problem is NP-hard. Therefore, we propose a polynomial time, greedy, and heuristic approach that consists of 4 phases: active slice in identification, request selection, edge cloud selection, and forwarding path selection. So in the first phase, that is the active slice identification, we identify a subset of active slices that can be redistributed or dropped based on a cost function. This cost function we design later, I present later. And this active slice identification enables control slice redistribution. So as we mentioned that we consider the control slice redistribution in the network. So this phase 1 ensures the control slice redistribution in the network. Then we focus on the request selection. So where we identify the sequence of the request to be served in the network. And in the third phase, for a given request, we select an edge cloud with minimum cost considering slice specific requirements. So again, we design another cost function to select the edge cloud. And finally, for the given request and the selected edge cloud, we select the forwarding path for traffic routing associated with the slice. So now let us go through each of these phases in detail. Yeah, so we design a weighted cost function for slice request that takes into account the bandwidth, storage, and compute costs. And here we have predefined constants alpha, beta, and gamma. These are used to capture the relative importance between the bandwidth, storage, and compute requirements. This BR, DR, and CR are the bandwidth, storage, and compute requirements by the slice request R. So again, to recall, the storage and compute requirements are calculated based on the VNFs associated with the slice request. We have Dmax, Gmax, and Cmax. These are the maximum bandwidth, storage, and compute requirements from the set of requests, respectively. So using this cost function, in this in the first page, active slice identification, we sort the active slices, active slice request using that cost function and the reward, and we earmark a subset of requests for potential redistribution. And in the second page, the request selection page, we sort the new and identified active slice request based on the reward and the cost function presented earlier. And we check each request for admission from the sorted list. So let us try to understand these two phases using this example. So we have, let us say we have active slices that are sorted based on the reward and the cost function. So we have 3, 5, 1, 4, 2. These are the active slices in the network. And we allow 40% active slices can be redistributed. So these 40% slices are considered for potential redistribution. So here we identify the slices 4 and 2 for potential redistribution. And we these 3, 5, 1 are untouched, that are being served in the network. And these identified active slices are included in the set of new requests. So now, so let us say we have received 6, 7 as new request in the current time slot, and we include these 4 and 2 as the part of new request. So we have 4, 2, 6, 7 as the new request. Now from this set of new requests, we sort this request based on the reward and the cost function, and then we check the request for admission in a sequentially. So request 4 is checked first, then 6, then 2, and so on. So once we have a request which is identified for admission, then we need to focus on the edge cloud selection in the network. So
Samaresh, one question. What was the ratio in the previous slide?
Sorry?
What was the ratio? What does ratio mean in the last slide?
Okay. This is the ratio between the reward and the cost. So,
okay.
So the reward is the jitter and.
Okay.
All right. Yeah. Okay. Thank you. Yeah. So next we focus on the edge cloud selection for the given request. So similarly, we design another weighted cost function that contains this bandwidth, storage, and compute cost in the network. And here we consider the bandwidth of incoming links to the edge cloud. So this ensures that we have more aggregated bandwidth to reach the particular edge cloud. And similarly, we have alpha, beta, and gamma. These are predefined constants used to capture the relative importance between the bandwidth, storage, and compute cost. And we have dk and ck is the storage and compute resources at the edge cloud k. And we have the residual resources such as bandwidth at the links, storage at the edge cloud k, and compute resource at the edge cloud k. So based on this cost function, the edge cloud with the minimum cost is selected to serve the particular request. So let us say we have different edge cloud IDs, and the cost is determined based on this cost function. And the edge cloud 2 is selected as it has minimum cost. So yeah, another thing is that if we don't have any candidate edge cloud in the network, then the request is dropped. That means it's not considered for admission. So now for the given request R and selected edge cloud with minimum cost, we need to select the forwarding path. So to select the forwarding path, we obtain a residual network, and then we apply the Dijkstra's shortest path algorithm for the forwarding path. So let us look at the example here. Let us say we have request bandwidth, requirement is 5. So we are given the network with the selected edge cloud, and this is the source at the edge. So this is not the original source, but this is the source at the edge cloud. Now we need to determine the forwarding path. So the links that do not meet the required bandwidth are pruned, and then we apply the Dijkstra's shortest path algorithm. And here the link weight is calculated as the ratio between the initial bandwidth and the residual bandwidth of the link. So again, if no path is found, the request is dropped. And finally, we update the networking resources, the bandwidth of the links, compute, and storage resources at the edge cloud. Now we move to the performance evaluation. So to evaluate the performance of this proposed scheme, we use a quadratic penalty function. That means the more number of slice redistribution, the larger is the penalty. However, we note that any penalty function can be used to capture this the effect of active slice redistribution in the network. The values of the parameters used in the for the performance evaluation is considered from the literature. and the predefined constants are chosen manually. The predefined constant for the request selection and edge cloud selection are chosen manually. The first part of the result is the comparison between the optimal solution and the proposed scheme called reset. So we obtain the optimal solution using the IBM CPLX solver. We have two variants of the proposed scheme, one with the 5% 5% active slices for potential redistribution, and another one with the 10% potential redistribution. We have percentage of edge clouds 10%. That means the 10% nodes in the network are selected as edge clouds. So the edge clouds we select as in their order. So the node with the highest order is selected first, then the second one. In that way, we select 10% of the nodes as edge cloud. We select the total number of requests as 500 slice requests in the network that are coming into different time slots in the network, and they follow the Poisson process. And we use two penalty factor, 0 and 0.5, the penalty factor sigma. So here we use two different penalty factor. So first we obtain the plot the total reward. So in the x-axis, we have arrival rate, that is the number of requests per second. And in the y-axis, we have total reward. And we have three different schemes, optimal solution, and the two variants of the proposed scheme, one with the 5% slices for potential identified as active for potential redistribution, and another with 10%. And we have two variants of the penalty factor, one with 0 penalty and the other one with 0.5 penalty. And eta is the 10%, so percentage of nodes selected as edge cloud. So for both the figures, we have 10% nodes selected as edge cloud. And from this figure, we see that the proposed solution reset is competitive with the optimal solution, and the total reward is within 15 to 25%. Further, we see that the total reward decreases with and increasing in the arrival rate. This is because the more number of requests arrive at a particular time slot, but due to the limited resources, bandwidth, compute, and storage resources, the request cannot be served. So we have less reward in the network. Okay, then we plot the slice redistribution in the network. And similarly, in the x-axis, we have arrival rate, that is the number of requests per second. And in the y-axis, we have percentage of slice redistribution in the network. We have three different.
One more question.
Yes.
So if a request cannot be accepted, is there any penalty for that?
No, we don't consider any penalty. But yes, we can consider. But in this work, we do not consider.
Okay, fine.
No, thank you. So we have three different. So another point I would like to note here is actually we are extending this work. So if the request cannot be served by the edge network, then we can send it to the core network. So in that way you can serve, but here we do not consider any penalty.
But then depends on the type of request. If your delay requirement is stringent, then the core sending it to the core may violate that. So
yes. So again, yes. So we need to consider the QoS requirements as well. Yeah.
Okay.
So yeah. So similarly, we have three different schemes: optimal solution and the two variants of the proposed scheme. And yeah. So two penalty factors: one with 0 penalty and other one with 0.5 penalty. And we have 10% nodes as selected as edge cloud. So we see that from both the figures, the proposed scheme reset entails far fewer slice redistribution compared to the optimal solution. And another interesting thing we notice here is that using the optimal solution, the slice redistribution decreased with increased penalty. So here it was about more than 100% in some cases, but when we have increased penalty, the percentage of slice redistribution is decreased. Then we plot the computation time. So as the optimal solution is obtaining optimal solution is NP-hard, so the computation time is very large. So in the x-axis, we have arrival rate, that is the number of requests per second, and in the y-axis, we have computation time in seconds, and we plot it in log scale. Similarly, we have three different plots. One is for the optimal solution and two variants of the proposed solution. And we see that the computation time of the proposed solution is smaller by 2 orders of magnitude than that of the optimal solution. So our takeaway here is that we have a smaller computation time. We have a very small percentage of slice redistribution, but competitive reward with the optimal solution. Yeah, so then we evaluate the performance in a large scale deployment, because when we increase the percentage of edge clouds to 20%, it was taking a very long time to solve using the CPLX solver. So we use this 10% and 20% nodes as edge cloud for large scale deployment. And we compare the proposed scheme with the two benchmark schemes. One is the reward and another one is the FCFS. So as the name suggests, in case of reward, the requests are prioritized for admission based on their reward. And in case of FCFS, that first come, first served basis. So the requests are prioritized for admission in the order they are received by the network operator. And we consider the percentage of slice percentage of active slices for potential redistribution as 5% for all the schemes, the proposed solution, reward, and FCFS. So we plot the reward obtained by the using all the schemes. In the x-axis, we have arrival rate, that is the number of requests per second, and in the y-axis, we have total reward. And we plot three different schemes: the proposed scheme, reset, then the reward, and the FCFS. And we have four different scenarios: one with 0 penalty, 10% nodes as edge cloud; 0.5 penalty, 10% nodes as edge cloud; then 0 penalty, 20% nodes as edge cloud; and 0.5 penalty, 20% nodes as edge cloud. So in all these scenarios, we see that with more number of edge clouds in the network, the reward increases. And another thing we notice here is that the proposed scheme reset achieves a higher reward compared to the benchmark schemes. This is because the proposed scheme reset considers the bandwidth, compute, and storage requirements, as well as the reward associated with the request. So that's why we are able to obtain more reward compared to the benchmark schemes.
Then, sorry, one question. Yes. What does it mean when this 10%? It means 10% of the nodes are like edge clouds. Are they?
Yes. Yes.
What does it mean that the nodes, 10% of the nodes are capable of housing VNFs? Is that the meaning of it?
Yes. Yes. So that are these 10% nodes are facilitated with some compute and storage resources, so we can place the VNFs.
Okay. Other nodes cannot host VNFs.
They simply forward. They cannot host the VNFs.
Okay.
Because just we cannot deploy all the nodes as edge clouds. So some of the nodes are treated as edge clouds, and other nodes, they simply forward the traffic in the network.
Okay. So if a node is capable of running a VNF,
yes,
if it has enough resources so that VNF can be run, then you're calling that node an edge cloud. Is that
yes? Right? Yes. Sir.
Okay. All right. Okay. Fine. Go ahead, please.
Yeah, Samaresh, I have a question.
Yes.
So when you say 10%, so you are choosing randomly random nodes in the network to be edge clouds, or is there some in the network, the nodes which are in the periphery, those are only taken as edge nodes, or there are any random nodes?
No, it is not random. We select it as in the order. So suppose a node have more number of neighbors, so based on their degrees, basically outgoing degrees. So
So when you change the, so suppose initially you have taken all 4-degree nodes to be edge clouds, and then you, did you try changing to say 3-degree edge, and how does the answer changes if there is a difference in the choosing of the nodes?
No, that we didn't check, but we evaluated the performance using 2 different topologies. So we observe the similar performance. I mean, so the value changes, but the pattern is the similar.
And in both the topologies, you took, for instance, 4-degree and above nodes to be the edge clouds.
Yes.
And one more question: when you change the percentage from 10 to 20%, so making a node as edge cloud itself brings a cost with it. So when you increase the number of nodes from 10 to 20, so you, as you mentioned, the reward will definitely increase. But so is the reward much higher than the cost of implementing, say, 10% more edge clouds in the network?
Okay, so yeah, to be honest, I didn't give a thought on this, but yeah, you were right. So like we have to find out the trade-off between this percentage of edge clouds and the reward. Suppose, yeah, if we make it 30%, we may be able to accommodate like admit more number of requests, but the deployment cost may be more. So yeah, you are right.
Yeah. Okay.
Yeah. Okay. Thank you. So may I go ahead?
Sure. Please go ahead.
Yeah. Thank you. Yeah. So now we plot the slice redistribution. So in the x-axis, we have arrival rate, that is the number of requests per second. And in the y-axis, we have percentage of active slice redistribution in the network. And similarly, we have 3 different schemes, the proposed scheme reset, then the 2 benchmark scheme, reward and FCFS. And we have 4 different scenarios, like 0 penalty, 0.5 penalty, and 10% nodes as edge cloud. Then 0 penalty and 0.5 penalty, 20% nodes as edge cloud. And from all this figure, we see that this scheme, FCFS, entails fewer slice redistribution in the network compared to the proposed scheme reset and the reward. This is the reason, this is because the FCFS scheme admits the request in the order they are received by the network operator. So even if we consider some of the active slices for potential redistribution, they are prioritized first for admission. So that's why we have low slice redistribution percentage for the FCFS scheme. Yeah, so as summary of this work, we proposed a 5G edge network slicing scheme with controlled active slice redistribution that accounts multidimensional resources such as bandwidth, compute, and storage resources in the network. And we see that the proposed scheme reset yields a competitive reward to the optimal solution while incurring far fewer slice redistribution, and the computation time is also smaller by 2 orders of magnitude. And we also see that the proposed scheme reset achieves more reward than the 2 benchmark schemes. And yeah, so this one, this particular work has been accepted in the CNSM conference. And please do read our paper for additional details. Yeah, so now as part of the current work, we are focusing on end-to-end network slicing that comprises of 5G radio access network, edge, and core network. So at the radio access network, we are considering the resource block available at the RAN. Then at the edge and core networks, we have edge cloud and the central cloud respectively. So the edge cloud and core central cloud are facilitated with compute and storage resources, whereas this RAN, we have the physical resource block. So now we are focusing on this end-to-end network slicing. And we are using the Bayesian optimization for automatic tuning of predefined constants for the cost function. So if I recall, we have for 2 different cost functions, we have alpha, beta, gamma. So in the work that we did, there we considered the values, we manually tuned it. However, we can use the Bayesian optimization for automatically to automatically tune those constants. And after tuning this parameter the predefined constants automatically, we see that the proposed solution is within 10% with the with the optimal solution. And once we have this auto-tune thing, the proposed solution will be independent of network topology, network resources, and the slice request. So we are working on these two things. And parallelly, we are also working on software prototype implementation of network slicing in 5G. So where we are using OSM, open source Mano, for automated network management and orchestration. And to deploy the 5G core network functions, we are using Free5GC, all are open source. And to simulate the 5G radio access network and user equipment, we are using uRLLC. So once we have the end-to-end network slicing in 5G, so we will have something like this. The OSM will control all the entities in the network. So where we will have 5G RAN, edge computing, and the central cloud. And this connectivity, the traffic routing between these different clouds and the RAN will be managed by the software-defined network controller. And this virtual network infrastructure manager and virtual network function manager will be controlled by the network function virtualization entity. So we are working on this, and this implementation is very preliminary stage, but yeah, we are hopeful to have the basic setup ready soon. So yeah, and finally, I would like to acknowledge the Department of Electrical Communication Engineering and the Center for Network Intelligence for supporting this work. And yeah, thank you. So that's all from my side. And yeah, if you questions, please.
So Samaresh, one question.
Yes.
This is about the last close to the last slide. You had this point about automatic tuning of the constants.
Yeah. Mm-hmm.
So here, if I take that example with alpha, beta, and gamma as the constants,
Mm-hmm.
then when you set it manually,
mm-hmm.
what are the considerations? On what basis do you set them?
Okay, so for example, we set it as like for eMBB request, for the mobile broadband request, we have the bandwidth is more. So the bandwidth requirement is more. So we have more importance on the bandwidth than the storage and compute.
Mm-hmm.
So then for you low latency, ultra reliable and low latency applications, we considered is, I don't remember the exact values, but based on that, which one is more important than the others. Mm-hmm. So based on that, we tune it.
Okay, so these constants will determine the reward, is it?
Not the constant.
So what was the reward was a function of all of these? No, what was the reward was the revenue. Mm-hmm. And what were, just remind me again of what the role of alpha, beta, and gamma were.
Okay, so alpha, beta, gamma, it basically adjusts that which request we should serve first. So suppose a request reward is 5, but the bandwidth, compute, and storage requirement is very high. Whereas for another request, the reward might be 2, that is low, but also its bandwidth, storage, and compute requirement is also low. So in that case, we prefer, for example, the request with reward 2, not the request with reward 5. So which one to prefer first, that is decided by the cost function.
Okay. And then when you want to tune it automatically, then again, for a particular type of application, like for example, enhanced mobile broadband, what will the logic be? How will you arrive at one set of parameters, and how will that change?
Okay, so yeah, I think one thing I didn't mention. So this alpha, beta, gamma. Yeah, so this alpha, beta, gamma, we have a total 9 set of parameters. So alpha like alpha eMBB, alpha uRLLC, and alpha mMTC. So likewise, we have 9 parameters for this request selection. So so in that way we select it, and when we automatically tune it, how we did it is as like we generate the request as based on the Poisson process, and then we tune it like which parameter set of parameter gives us the highest reward, and we take multiple runs. So 50 samples we take, and from there we average it, that which combination gives us the highest average reward.
So this computation is done on the fly as requests are coming in.
No, sir, we cannot do it because actually this concept of Bayesian optimization comes from this machine learning thing, that hyperparameter tuning. So it involves very much computation time. So we cannot do it on the fly. So we have to tune it before then we can apply it to the network.
Okay.
So for example, for this small setup, like this 9 parameters, and for edge cloud selection we have 3 parameters. So for these 12 parameters, it was taking like for single run, it was taking few hours. So we cannot do it in real time.
There was one slide in which you were showing some percentages, and something was more than 100%. Can you just repeat? Yeah, what was that?
Yeah, here. Yeah, so the requests are coming in different time slots. So at each time slot, beginning of time slot, we are taking the decision that which request to consider for potential redistribution and which one to serve. So in that way, we see that some of the slices, like slices are redistributed multiple times in different time slots. So and it is more than 100% because here the arrival rate is very low. So we have more number of time slots because we considered 500 requests to be arrived. So that are like number of time slot is very high. So in that way, number of slice redistribution is also very high.
Achha. Okay. And one last question.
Yeah.
When you use the Cplex solver to obtain the optimal solution, do you know what algorithm Cplex is using internally to get the optimal solution?
So it was using branch and bound.
Branch and bound.
Yeah, so we didn't tune the optimality gap. So use the default optimality gap, but it may be reduced when if we increase the gap.
Okay. Okay. Thank you.
Thank you.
Just one question, Samaresh.
Yes.
You can go back to that alpha, beta, gamma REQ. You had a constraint that was set to equal 1.
Yes.
So somehow this is basically forcing the equal comparison across the different types, because you have something for eMBB and so on. So somehow you're balancing it across them. Is it better not to keep this at 1 and then maybe tune the relative importance of those as well?
Yes, actually, here we considered as 1, but when we are automatically tuning it, then we do not use this bound, so not equal to 1. So we keep it open that alpha, beta, gamma can be any value from 0 to 1. So they take based on their importance.
Okay, all right. Thank you.
Thank you, Samaresh, for the informative talk. We can take 1 or 2 more questions before we close the session.
Samaresh, Preetham here. One basic question. In this bandwidth cost and compute cost, this Bmax in the denominator, that is the maximum across all slices or the sum?
No, this is the set of requests received at the current time slot. So we do not consider all the requests. So suppose we have 5 requests that needs to be admitted in the network. So the maximum requirement from that particular that set of requests, 5 requests.
Okay, thank you. And one more question. In this NFV placement, do you also consider the distance cost in the calculations, that like the network cost of reaching that NFV from the source of the traffic? Say, for example, if it's a CDN kind of traffic.
Okay, just I think just a minute. Yeah, suppose I think you are asking that we can place both the VNFs for suppose here, right? Is it so? Or?
Right. Yeah.
Yeah. No, we don't consider, but here we consider the fact that all the VNFs are placed at the single edge cloud, not at multiple edge clouds. So we do not consider the distance.
Yeah, but the second question is like related, is that even if you keep all of them together, the cost of reaching the VNF from the whatever endpoint, is that a factor in your decision?
No, we didn't consider that fact, that thing, but yeah. So do we have? Yeah, obviously it will increase the routing cost, because suppose we can place here and we simply go ACF instead of ACDEF. So it will increase the routing cost. So the bandwidth will be an issue if we have like long distance path. But in our proposed solution and the model, we didn't consider.
Okay, thank you.